sunflowers. So I have not so much time, but I'm going to talk about some technical tools. So I'm going to make hand waving deliver of you to exact place where you want to use sunflowers. And exactly with hand waves, I'm going to finish the proof. But at the same time, I really expect that if you want to see some details of the proofs that I present, you should ask me, and I will explain it more carefully. Okay, let me start with the definition of sunflower. Classical definition of sunflower. So we have collection of sets, and we assume that all of these sets of fixed size k. For many applications, we can think that we have upper bound on the size of these sets, not just fixed size, but size is at most k. And sunflower is a structure that's defined by a core. It's an intersection of all sets that we can see in the sunflower. And we have only one condition, that pairwise intersection of two sets is exactly the same as the core. So we can draw a picture like that. We have a collection of sets, and intersection is set in the middle, and all petals looks independent without intersection. Yeah, we really like the structure, and it's useful everywhere. But recently, by Rossmann, it was defined some generalization of sunflowers, so-called robust sunflowers. It's also a set structure, so we have collection of sets. Again, we can think about collection of fixed size or of size at most k, and we can define also intersection of all sets that we can see in the sunflower. And the last property. When I saw it first time, I thought, what is actually it? How can I read it? It's too complicated. Actually, it says that we want to sample some other sets from some distribution, and we will have some condition that some sets will intersect with other sets. And actually, there is a mistake on slide. The time should be this way. So W should be a superset. But don't worry if you cannot read it now. Like we will return to this definition later. Now it looks like too aggressive.
Is it a bit like the petals are random sets?
No. Like petal, we have some fixed collection of sets. Here, like it's given to us. We cannot fix.
No. But like, is the third condition like what would be true naturally if the petals were generated at random?
Yeah, we will go to this definition. Yes. So, and first time that I saw it, I asked somebody. I don't remember who it was. Why is robust sunflower is actually a sunflower? And I've got an answer. So if we fix some parameters. We will inside robust sunflower, we can find an actual sunflower. And I think that this person was a truly mathematician because it's precise answer, it's true, and it's useless at all.
Why is it not? I mean, why is the question?
Because the third condition looks ugly for me.
But the third condition is an additional condition.
No.
Missing the
additional condition.
This
just
it replaces
we completely replace the third condition.
Oh,
Yeah.
okay.
And why is it's useless? Because if you open any paper that uses robust sunflower, we do not use this lemma. We deal with robust sunflowers in different way. So today I'm going to explain why actually robust sunflower is the right object to think about, and I'm gonna do it via considering some examples. Yeah.
Dmitry, just to be clear, you're saying so what the third condition should be that there exists an I such that W is a superset of.
Yes. Yeah. Superset.
okay.
No, not subset, supersets.
Okay.
Yeah, sorry. It's
Just to confirm, W is picked by sampling elements.
W is picked by
Random.
yes. Yeah.
And including them with probability P or something?
Right.
Yes. Yeah.
So the intuition should be the petals are very small so that with high probability you
Yeah,
include them.
we will go to intuition, yeah,
Sorry.
yeah. Okay,
So-
Hmm?
No, so the elements are picked from the union of the S sets.
no, like here we have zero one strings and we pick one with probability P uniformly at random.
That's right. Yeah,
We will return to this definition later. Okay.
Just think about the unit.
So
Right.
let's start with some classical applications of sunflowers, and I want to start with lower bound on monotone circuits. It's actually the first place where I saw sunflowers. So we have monotone circuit, and we assume that this circuit should compute a click, and we want to show lower bound. Actually, I don't want to show the whole lower bound, but I want to show some specific part. So suppose we have an instance and no instances. And these no instances are generated by Erdős-Rényi process. So we pick a random graph on n vertices, and each h we draw with probability p, such that with high probability there is no click of some big enough size. And to show lower bound, we actually want to approximate our monotone circuit. And we want to use approximation via OR of indicator circuits. The whole strategy looks like we create this approximation for AND gates, we create this approximation for OR gates. And if on yes and no instances we introduce not so many errors, we can show in the end that OR of indicator circuits cannot compute actual click function. But now I want to show only on no instances, and I want to show how we will approximate OR gate. So originally we start from inputs of the circuits and go from inputs to the top gate. So we have already approximated a previous layer, and now we want to approximate OR of indicator circuits. Since we have OR of fixed size, but after approximation, we can get OR of much bigger number of indicator circuits. We want to shrink the number of indicator circuits. Let's fix some parameters. We assume that this indicator is trying to compute click of small enough size, k, and also we assume that our graph with high probability contain click of much bigger size. So if we want to order our parameters, there is parameter r that is much bigger than n to the epsilon times k, that is much bigger than. Okay, so we want to approximate it by OR of indicator circuits. So what's the picture we have? We have a graph, and we already have some number of indicator circuits that I draw here as sequence, and we want to approximate all of them. And ideal situation that we can have in our life, so we have a lot of independent indicator circuits. In this case, since we want to approximate all of indicator circuits, we can just replace it by one, because in our graph, actually, we know that there is a click of much bigger size. And since if you have a lot of independent indicators, this click will cover at least one of them with really high probability. What we can state in our ideal situation, then if we pick a graph that's randomly generated by our process, then with high probability there is some I such that this indicator will return 1. And in this ideal situation, we can just replace our OR of indicator circuits by one function. Does it make sense? Questions?
You assume that indicators doesn't intersect?
No, yeah, independent, without intersections, yeah.
By the picture.
No, not all of them, like just many of them are independent. Yeah. But what we can have in the real world, so now we cannot claim that all of these indicators independent, or even we can find some big collection of independent indicators. For example, all of these indicators may contain some single vertex. But we can use sunflower lemma that says that if you have big enough collection of indicators, we can find a sunflower inside it. So there is a sunflower with large amount of petals. So our indicators will form this picture. What we can say, instead of saying that, actually with high probability, our random click of bigger size will cover one of this petal, we can claim conditional statement. If we will cover the core of the sunflower, then under this condition, with high probability, we will cover at least one petal. Because now petals are independent. That's what we have. Yeah. So this is the picture that may happen, but with high probability, this random click will cover at least one petal. What can we do? Instead of replacement our function by just constant one function, now we want to make plugin operation. Instead of this sunflower, we'll replace all of them by the core of sunflowers, because we know that value of our or of indicator circuits will depend on the fact if we cover the core or not. Yeah. So this is it. And now we can see what we have in robust sunflower situation. If we consider the third condition now, actually we can rewrite third condition. Now it's correct. Yeah. If you rewrite third condition in slightly different way, it's exactly what we use here. So third condition just says that instead of independence of the petals, we just replace it by the fact that with high probability, our random process will cover at least one petal. And this is intuition, as what mentioned before. Yes, that's what we usually expect by normal sunflower, since we have a lot of independent things. But usually we even don't care if we have a lot of independent things. We care about this covering property.
The original proof, it is the original proof. It was more general when when the core is defined as any set such that after you remove it. So it covers all pairwise intersections, but not this. So in the definition of P epsilon robust sunflower, how important is the second condition? I don't see that it's very important.
It's not important for this application, and
will be important
for the last application today. Probably it will be important.
But most likely we can think about Z as something in our hands that we want to make as small as possible.
Yes. And actually, people study it independently, and it's called just flower without sun. And yeah, it's also useful. Yeah. That's right.
Okay, thank you.
Okay, so this is the right definition that helps here. So let me try to define some general problem. Like this is the first takeaway that I want to present. So we have some number of variables. And we have collection of events, and these events are monotone in our case. So these events are defined by conjunction of some subset of variables. And well, we know that this conjunction should be of fixed size, or we have upper bound on the size of this conjunction. And if we care about the question, what's the probability that we will satisfy at least one event? That's
what is random here.
Or random assignment. Random assignment to the variables.
Even completely random.
Independent. Yes. Now independence is important.
Unbiased or biased, it doesn't matter.
Usually biased, we set it to 0, 1 with some fixed probability, and this probability is the same for all of them. So ideal situation that when we can answer a question, if we have a lot of independent events, then we know that this probability is approximately 1. But in real life, what we can find only sunflower there. We can claim independence because, again, for example, all our events may depend on the first variable. And then plug-in operation can help us. Instead of replace this probability to 1, at least we can simplify the structure of our problem by using this plug-in operation. And new reality, so instead of usual sunflowers, we can use robust sunflowers. And since it's generalization, it's usually easier to find. We need much smaller collection of events that give us robust sunflower rather than sunflower. So, questions? Comments?
Do you also do weakening here? I mean that if you generate a set which is in a larger set, do you remove the larger set or not?
Well, I don't really understand.
Again, after plugin operation, it can be the case that some of your classes
Yeah,
are a subset of others, a little bit larger or whatever.
no, not so big difference. You can do it in both ways.
You can keep them, yeah?
Yes, you can keep them. Okay, so this is the key property of robust sunflowers. Let's consider it from a bit different way, but the same problem. So again, we have collection of variables and we have collection of terms. It's just conjunction. And we consider this property, but now what is it? We can replace it by or of these terms. So naturally we have just a DNF formula now. And again, we're asking a question with what probability it will be 1. So we know that if you have a lot of independent, we can replace it by 1. But what we can achieve by using sunflowers and robust sunflowers? There are a lot of papers about it. It's called CNF or DNF sparsification. I choose some random paper among all of this collection because it's really simple, but result is strong enough. There is stronger result than this by Lavette and Jung, and using this result, they actually get construction of robust sunflowers. But yeah, what's this theorem state? If we start with some WDNF, then we can replace this WDNF by another DNF formula of the same width. But the size of new DNF formula will depend only on W. It's independent of the number of variables. And these two DNFs will be close enough to each other. So this probability, you can choose your favorite probability. Why people interested in it? So there are many applications like algorithms for SATs, but in this particular paper they used to build some pseudo-random generators against WCNF formulas, and it's also related to Mansour's conjecture about Fourier spectrum of DNF formulas.
Does this have one-sided error?
They proved stronger that yes, it can be one-sided and you can choose it on both sides.
Right.
Yeah, but okay, our workshop complexity, instead of proving this theorem, I replace it by some proof complexity problem. I want to show lower bound on ResK. What is ResK? It's a resolution style proof system, but instead of like disjunction on each line, we can use KDNF. Our proof line are KDNF for fixed K. What I want to show? I want to show lower bound on random CNF formulas for some parameter K that is log n over log n. We know lower bound for these formulas. It's given by Alexander. It's exponential lower bound, but proof is really complicated. So we need some strong version of switching lemma.
It was not exactly a random CNF. It was not exactly a random CNF.
It also works for random CNF with small bits. Yes.
You say it works.
Yeah, yeah.
Thank you.
But I want to show simple proof. Like, no, for the original proof of exponential size, we really need to go deep into it to understand. But now I want to show simple proof, but quasi-polynomial size lower bound. Actually, it is a frontier for random CNF formulas. Even for log n CNF formulas, it's the best what we can achieve right now. Like for larger K, we cannot do anything. And for constant CNF formulas, even square root of logarithm is a borderline here. Yeah, so
Square root of logarithm where?
yeah, in K. Yeah, this is an open problem to improve square root of logarithm. In K, so for constant width CNF formula, random can you show lower bound for anything better than rest of square root log n. And in some sense, it is connected to a question about robust sunflowers. We saw that this condition on robust sunflowers, last condition, it holds over uniform independent distribution. And to improve like this theorem, the statement above, if you want to show it for constant width CNF formulas, we need it will be enough to build robust sunflowers against Hardy distributions. But let's prove lower bound. I'll give you a sketch. Maybe some questions about statement.
Now the last slide, I didn't understand what is the context of the open problems. We're talking about the theorem. You're going to give a simple proof with a weaker lower bound, and then you said the open problems. How are they related?
Oh no, theorem for log n CNF formulas.
Right.
But open problem for constant width CNF formula.
And how are they related to the theorem?
That's what we want. Improve complexity. We want lower bounds, but theorems theorem says that what we can do improve complexity right now.
Dima, why squared log? You are saying that for square log n it is known, right?
For square root log n, it's known. Yes.
Proved it.
In Olehnovich's paper, it's proved for square root of log n over log log.
Okay,
but
I will.
Viviv and Anastasia improved it to square root log.
I will compare it.
Okay. So let's do it. So general idea. Suppose we have a proof, and its proof should work for random CNF formula that is given to us. We do standard tricks in proof complexity. We hit a proof by random restriction. And we assume that this restriction of linear size, or it can be even smaller than linear. So we can think that we assign roughly n over log n variables. So small random restriction. We know that if you consider random log n CNF formula, then this formula almost won't be affected by this restriction. And this actually the place where we use that our formula has large widths. So if you consider a formula of small widths, we cannot apply a random restriction to it. Yeah, I mean uniform random restriction where we assign each variable independent.
Well, you still can if delta is a constant, right?
No, if you have constant with CNF, then yeah.
Because union bound does not.
Well, now the magical step, and we have wizard cat here that says that actually we hope that each line of the proof with high probability under this restriction will transforms into a line of the proof that depends only on square root n number of variables. If we believe in this statement, then we can say, actually, if we have this proof, then we can transform it into resolution proof. So each line depends on few variables, then we can transform it into resolution proof of the same width. Well, we don't care about size. Size may be blow up by 2 to the square root n, but width will be fine. And it remains to show lower bound on resolution width after. But since our log n CNF formula have not really affected by our random assignment, then we know how to prove resolution width lower bound. Pick your favorite technique and be happy with it. Questions about the sketch?
How you get lower bound?
Oh, yes. How we get lower bound? There is magical step. I want to say that magical step will be true with some probability. And if our proof will have small size, then we can use union bound and say that it will be true for all lines. Questions? Okay, so let's go to magical step. We have KDNF formula. And what we will do, we actually have nice tool, sunflowers, and our wizard cat also want to use it. So first of all, if n, so number of terms in our proof line, is bigger than square root n, we can do the following trick. First of all, we choose quasi-monotone subformula. You can use any way how to do it, and in particular, you can use naive way. So we have some DNF formula and pick total assignment. Each term in this DNF will be satisfied with probability 1 over 2k.
So just to double check, your ands are ors here, right?
Oh yeah, it's up. So each term will be satisfied with this probability. So if L, now we pick all terms that satisfied by total assignment, and only these terms, and it will be quasi-monotone formulas. Quasi-monotone means that each variable appear either with positive sign or with negative signs, but not together. Okay, so we have quasi-monotone subformula of size L over 2 to the k, at least. Because on average, that's what we see, that will be the amount of terms that are satisfied by total assignment. Questions, comments? Okay, so it's also roughly square root n because our k is small enough. Then we want to say, inside our quasi-monotone subformula, we can find robust sunflower on these variables. And what parameters on the robust sunflower we need? Here we use this almost the same delta that we used above, a little bit small. And we do again plug-in operation. So instead of this sunflower, we'll replace all terms by the core of the sunflower. I claim that after I apply random restriction, I will get the equivalent DNF formula for a single operation. Of course, I want to repeat it until L will be small enough. But since after each operation, size of this line reduced by 1, then total number of operations that I want to use here for all lines of the proof is bounded by the size of the proof. Yeah. Questions? Comments? Yeah. Okay.
Probability is over what? So
Over random restriction.
for the most restriction, they are equivalent.
For the most restrictions, they're equivalent, yes.
So in the end, the number of variables is root n times k.
Yeah, roughly like this, but k is small enough, so yeah, I just ignored it. Actually, here instead of square root n, you can use any polynomial. Yeah, it's not so important. It remains to show this claim, but so we have quasi-monotone subformula. that means that our random assignment will assign a variable to right value with probability delta over 2. Yeah, and we want to say that actually the tail of the sunflower what's stated here, that it's a claim that we cover at least one petal of our sunflower, and it's just a property of sunflower. So this is exactly the first property of the sunflower what we have. Yeah. Now we just claim that since we cover at least one petal with high probability, the value of whole DNA formula depends on the value of the core. Yeah, this is it. Some parameters that we want to fix here. So we want epsilon to be quasi-polynomially small. And that's what we can achieve from the best known lower bound for sunflowers. Yeah, from always Slavet and Jan paper. Here, instead of square root n, you can use your favorite polynomial. This constant kappa is a constant. This constant kappa depends on this square root n. If you use here n to the epsilon, this kappa, you should take your kappa small. So we proved lower bound for res k, and that's actually the state of art, state of the art. Well, we can prove exponential lower bound, but at least it's super. Questions, comments?
Can you explain again the quasi-monotone?
Oh, no, quasi-monotone means that each variable appear either with positive sign or with negative sign, but not in this state.
That each variable is in each term, or
No. In the whole of this formula.
yeah, and how do you know it? You say pick this, and how do you know it exists?
Yeah, so you consider our whole DNA formula. Pick total assignment. So each term will be satisfied with probability 1 over 2k.
Right.
That means on average we will have L over 2k terms satisfied.
Okay.
We pick only those terms that are satisfied by sum total assignment.
Voice.
So if our L is bigger than square root n, then there is at least one quasi-monotone formula of size square root n over something small. Because k is small, it's smaller than logarithm. More questions? Oh, it looks like I have time for one more application. Yeah, and these are here again. We do not care about definition of the core. We can pick as a core. We can pick any superset of actual core, and we still will be happy. So I also want to show some depth lower bound on the circuit, and that will be so-called top-down depth lower bound. That was Jochen mentioned. But I want to show some weak lower bounds. To show this lower bound, I need to introduce some definitions.
What do you mean by that?
No, lower bound for depth 3 seconds. We will show lower bound for size, but for depth 3 seconds. Thank you. So first definition that I need is a definition of k limit. Suppose I have some formula, the KDNF formula, and I can consider set of satisfying assignments of this formula. Is there any structure? What can we say actually about the set? And there is some definition that help us to give some description. it's a definition of K-limit. So what is it? We want to say that some point is a K-limit of our set. Actually, if we cannot open few coordinates of this point and distinguish it from the whole set. Let me give an example. So here we have set A. Rows correspond to lines. And my claim that this point is a free limit. What does it mean that we can distinguish it by consider it, in this case, free coordinates? That means that if we can open some subset of free coordinates, like this one, we can find some point in our set where we will see the same thing. But this point itself is not in the set. But for any free coordinates, we can find it. For example, if we open first three coordinates, it will be 1, 0, 1. So last string will be Venus. Does it make sense?
You start with a CNF.
CNF or I did not state the claim. I wanted to do it now, but probably you will be correct. No, yeah, I want to say that claim that I did not put on the slide. Claim is the following. So, if our DNF formula accepts the whole set A, then
CNF.
Okay, yes, sorry. Yeah, instead of DNF formula, I should use here CNF formula. Yeah, so if our CNF formula accepts the whole set A, then it should also accept K-limit, any K-limit. And why it's true? Well, yeah, let's deal with CNF formula. Difficult. So if our formula accepts the whole set A, that means that some term should separate the whole set A from this K-limit. But yeah. That does make sense? So some term should give us different value for the whole set A and for K-limit, but it's impossible because this term may query only K number of variables, and since it should accept the whole set A, that means that for this particular coordinates that we can open here, it should return 1. But if this term query last three coordinates, then it should return 1 because in A we have this point, and it also should. That means that it also should return 1 on free limit. Actually, it's true in both ways. So some set is some set that can be accepted by some CNF formula if and only if this set contains all of its K-limits. In some sense, it's full characterization of the sets. Okay, and now I want to use this notation to show the free lower bounds. But for doing it, I need one more object, so-called spreadness, spread sets. What is the spread set? We want to say that X is again some collection of sets of size K. I do slightly different definition than usual, but not so big difference. That's just for sets of size K. I want to say that this set is delta spread if for any subset of coordinates, I can see ones in this position, not really frequent. So what does it mean? That means that this is a set X. I can open some coordinates, and if I pick random point, this event is not really frequent. not really frequent means that it's not much bigger than I expect to see if X contains all possible sets of size K. Not much bigger than you can see some delta parameter here. Delta, if delta is 1, is more or less the same probability as we see for all possible subsets of size K. But this set looks like almost, at least locally, it looks like whole set. Questions about definitions? Okay. And in fact, it's one of the key objects if you want to build actual robust sunflowers. We know that if we consider spread set, then itself it is a robust sunflower with empty core. Yeah, it's not so easy to show. It's not, but it's the same, not so hard. We need some either Chebyshev inequality, or if you want to prove stronger lower bound, some Janssen inequality. But yeah, we need to deal with second moments here. Yep.
Empty core in particular implies that the intersection of all sets in X is empty.
No. We just, it's robust sunflower. That means that if we pick a random subset, not from X, just random subsets where we pick each element with some probability,
All right.
then with high probability, we cover at least one element in X. But potentially there may be some intersections.
What does it mean, empty core?
Oh, intersection of all elements of X is empty. In X is empty.
I'm asking why.
Oh, intersection of all elements, but not pairwise.
Yeah, why?
Hmm?
Why? Is it difficult to see from their definition of delta squared why it is empty?
Oh, so suppose intersection of all elements in X is not empty. It means that we have the line
Yes.
full of ones.
Yes.
That means that probability that
It will be
probability will be 1 here. But here it's stated that no, it should be like small probability. More questions?
In fact, is a quantitative bound, right? It shows that the number of sets that could contain any given element is in fact something like n over k to the size of the set.
Yep. Yeah, for some cases, here you see there is some imbalance situation between zeros and ones, but for some applications, it's worth to consider like balance situation when we care about zeros and ones in the same way. Okay. I want to say that if you have some spread set, we know how to find the limit. Suppose we have some collection of points of size k, and we know that this collection is spread collection. Then my claim that 0 will be a good enough limit for us. It's more or less trivial statement. So fix some set of size at most k. K is bounded by this parameter, k limit. So for each element inside the set, we know that the probability that a random element in X will give us 1 in this position is really small. Then you can see the computation on the slide. That means that we can apply union bound and says that actually the probability that we will see 1 in at least one position in all of these sets is smaller than 1. That means that in X at least there is one witness for this set of coordinates where we can see only zeros. That's a definition of a k limit. So we cannot distinguish 0 point from this set by considering local like small number of coordinates. Questions, comments? And by using this fact, I want to show some lower bound on parity function. That parity requires depth-free circuits of exponential size. And in fact, it works not only for parity, It works also for big collection of partial functions, technique that I wanted to present. For example, we can extract some good functions that will imply oracle separations for some classes. So for the last result, we need to show lower bound not for parity, but for function like this. So we have Boolean Q. Our function is defined on sets of size smaller than this number. So here is 0. But collection of 1 points is defined by n to the delta. Here, between these points, our function is undefined. So here is we have just slice, but here we have the whole block. So if you technique that I want to present works for this partial function defined like this, and from this we can extract also lower bound oracle separation for some classes.
There's no switching lemma for this.
Yeah, no switching lemma, no restrictions at all. Okay. So can consider some depth-free circuit. And this is our top gate. I also need some help of the wizard cat, and the wizard cat came and says that instead of general circuits, I can consider circuits such that my top gate is connected to n to the epsilon DNF. It should be DNF here. Yeah, it's DNF. So, but there are some standard techniques how to reduce general circuits to circuits of this form. We can use any of them. Now I want to show lower bound for this type of circuits. And my parity function, now I deal with parity, it should return some zeros somewhere, and it should return ones on other points. If it is true, so suppose I have short circuit that can do this computation, I know that at least one of these DNFs should separate big fraction of zeros from all ones of parity function. Okay, so now I want to consider some point and consider some sphere around this point. I don't care where is this point. I draw it on the red part, but it can be anywhere. But I want to pick the point such that intersection with the white part will be as big as it can be. So what do I know about this point and the sphere? Let me fix some radius of the sphere that I draw here. And I want to say that actually intersection of the set y with this sphere, well, is what I can achieve from averaging argument. So it's like 2 to the minus n to the epsilon times the size of this sphere. Without loss of generality, let me assume that actually center of the sphere is 0, just for simplicity. Okay, what actually can I do? I want to use this spreadness result that allows me to use k-limit. So if I know that actually this thing is spread itself, then I can say something about the center of the sphere. Then I know that, in fact, any gate, this gate, if it accepts, if it rejects the set y, it should also reject the central point. If this set is spread, the only problem that this set may be not spread. But if the set is not spread, I know that for some coordinates I can see one there really frequently. There is some witness actually that this set is not spread. So let me pick the largest set I that violate the condition of spreadness. Yeah, now I want to say some technical point that in fact, if my center of the sphere with flipped bits I satisfy the condition that parity of AI is 0, I want to add one more element to I, but let's ignore this condition for now and talk about it a little bit later. So now I just consider some set, the largest set that violate spreadness condition. And I want to consider the set Y prime. Let me draw a picture. We have point A, we have sphere, and we have some intersection with Y. Now I consider some part of this set. So I consider only this sequence, where I know that bits on the coordinates that correspond to the set I are all ones. So here I know the condition that I xi my claim is actually now, if I consider this set will be spread. If I forget about I coordinates. So why is it true? If some other set of coordinates here violate the spreadness condition, I have a contradiction with the fact that I picked the largest set I. So if this set violates spreadness contradiction, I found set I in wrong way. I need to consider some bigger set I before. Questions? Comments? Yeah, so now I found the spread set. I found the spread set inside set Y. Well, by our statement about spreadness, I can claim that center of the sphere should be a K-limit. Well, but we forgot about set I, so I want to flip bits on the positions I of center of the sphere, and it will be a K-limit after. So because we have technical condition that you can flip one more bit and also take care about parity of A to the I. That means that we found a K-limit, and moreover, this K-limit should have a different value as a set Y. So we found K-limit in red region. But so now we can say if our n to the epsilon DNF returns 0 on the whole set Y, we found the point where our n to the epsilon DNF will return 0 also in the red region. So we found a mistake. Okay, yeah, so last what I want to say, that spreadness itself, we can think about it as a robust sunflower, but from time to time, it's much more useful to even think about spreadness itself, because we can use some properties like witnessing of violation condition of spreadness, and we can use it in our combinatorial proofs. And yeah, spreadness itself may be useful. So yeah, now I hope that our robust sunflowers are not so angry anymore.
Yeah, so in this previous group, where do you use the width into that?
I used, because here I can bound only k limit, but bounded k limit. So it's not like n limit, it n to the 0.45. So here I just need some fact that n to the epsilon is less than epsilon is less than 0.45. This is
So the size of I doesn't matter.
size of I doesn't matter. But at the same time, size of I will be small. We also controlled. Size of I will be smaller because this width, when we consider this subset, and we forget about I coordinates, we increase the density of the set in small universe. So if the density of the original set was big enough, then we also can bound sizes. More questions?
Thank you so much.